Okay, hi everyone. Thanks for joining us. Today we're going to work on solving logarithms. Now, this is a popular SAT question. We'll be using this in calculus. We'll be using this in pre-calculus. And it's one of those techniques that, again, we went and solved for basic x values, right? And then we solve for exponents. And now, I'm sorry, like x squared. And then now we're going to solve for what if the variable was in the exponent. So we take a look and we look at some problems like something easy. Let's start off with that. If we say something like, what is 2 to the x power is equal to 8. Okay. And in your brain, hopefully you're thinking, well, 2 to some exponent, 2 times 2 times 2 times 2. 2 times 2 times 2 times 2 times 2. That's what we're saying. We don't know how many twos we need because that's our variable. Now, how many twos do we need to get to 8? Well, 2 times 2 is 4, and then 4 times 2 is 8. We need 3 twos. So this is x is equal to 3. Now, we've already developed a couple ways of solving it. Now, with a calculator, we can say, well, 2 to the x equals to 8. We can say, actually, no, let's do our identity first. Circle of logs, log, what's my base? Is it 2x or 8? Log base 2 of 8 equals to x. So remember, this was my exponent. Log solve for exponents. So I always write the exponents on the other side of a log. So if I rewrite this, I can type this on my calculator. If you have a $10 calculator, you could definitely see what this is. You can just type it as it is. If you look at your calculator, you might have like little boxes, or it might say x and y. If you don't, we can separate this into what we call a change of base. So log of 8 divided by log of 2. And you should also end up with the same answer. And this answer is going to be 3, like what we expected. Okay. So we can do this using identities. We can do this algebraically using inverse operations. So here's another method of solving it. So if we say 2 to the x equals to 8. Now, the other method that we're going to learn today is logging both sides. So if I log one side, I'm going to log the other. If I log one side, I'm going to log the other. So it's almost like if I multiply one side by 3, I'm going to multiply the other side by 3. It's very simple, this idea of this algebraic operation. Now, what happens to logs when I have an exponent? And that's what the biggest deal about logs were. What happens to this exponent when I'm logging it? And hopefully you remember, logs bring down the gods. Logs bring down exponents. That's the main purpose of this log. X log of 2 is equal to log of 8, right? Because the x is in the exponent, and logs, whenever you're logging some with the exponent gets moved to the front. And that's a free move. Now we have log 2 and log 8. These are both just simple numbers, some type of irrational number, some type of decimal number. So I'm going to just divide them over. So divide both sides by log 2. Divide both sides by log 2. X is equal to log of 8 over log of 2. Does that look familiar to you? Hope it does. So this is like our algebraic way of breaking it down. So we have 3 different methods of solving this log, right? Any of these are totally valid. Some are easier than others. We have our one, just guess and check. What would that, how many 2's do we need? Hey, we need 3 2's to get 8. The answer is 3. That's how many we need. The other method is to use our identity, rewriting this to solve for exponents. This is our identity, changing it to log form, from exponential form to log form. And then the third way is this algebraic form, where we do the inverse. To get rid of the exponent, we're going to log both sides. All right, we're going to log both sides. And when I log both sides, the exponent gets brought to the front. So what I can't reach with my hand because it's too high, I go get a log ladder, and I can bring that the object on top down. Here's my log ladder, okay? My log ladder. See, it's like a ladder. See, it's gonna help me reach up and go get the x. Okay, log ladder. Okay, so what if this problem becomes a little harder? Let's go ahead and look at another problem. What if I say 2 to the x plus 3 is equal to 8 now? Okay, now this becomes a little harder, a little bit, because this x plus 3 kind of messes up with the way I count. Okay, I count 1, 2, 3. But imagine if I made you count every time you add 1. Every time you say 1, you have to add 3 to it. Say 2, you have to add 3 to it. Say 3, you have to add 3 to it. It's almost like traveling from different time zones. If you ever travel to New York, you think, okay, this isn't the same time in LA because they moved the time 3 hours different, right? 3 hours forward. If you go from New York to LA, your time zones change. If you go to the other side of the planet, like Japan or China, again, those time zones are shifted. So in order for us to deal with this in an easy way, instead of having to deal with that time zone shift, we're going to rewrite this. We're going to keep the same base. How can I get 2 right here? How can I make this into a 2? Well, similar to what we did before. So isn't 8 really 2 times 2 times 2? I'm going to rewrite this. 2x plus 3 is equal to, how many 2's are in 8? 2 cubed. So this is a way of doing it by factors, right? We're coming up with 8, and hey, can I make 8 look like 2? Well, I can. That's 2 times 2 times 2 is 8. Now, please take a look here. The bases are the same. If the bases are the same, that means the exponents have to be the same. So I'm writing it so that if the bases are the same, the exponents are the same. That means x plus 3 must equal to 3. So what does x have to be? We can do some algebra steps here. All right. So this can be done without a calculator. And on SAT questions, or non-calculator portions, where they want you to do steps like this to figure it out. How can I solve this without a calculator? Now, this problem can get a little bit weirder. What if I write 27 is equal to 9 to the x? Your natural inclination, I would say, is to say the answer is 3, right? Oh, sorry, I should have checked this other one. 2 to the 0 plus 3 is equal to 2 cubed, and 2 cubed is 8. So if x was 0, we'd be winning, okay? So this next problem, 27 is equal to 9 to the x power. This one is, 9 times 9 is 81. Oh, crap. That's not going to give me 27. What's the square root of 9? Square root of 9 is 3. Okay, that's not 27. So here is our trick. What numbers can I see that I can multiply to get 27 and I can multiply to become 9? So what is the base of these numbers? So I can rewrite this to become, well, 27 is 3 times 3 times 3. Yeah, 3 to the third. Perfect. So 3 to the third. And 9 is a 3. It's 3 squared. Now, if you take a look at how I'm going to write this, I wrote it in the parentheses because 9 is 3 squared, 27 is 3 cubed, and the x is an exponent of 3 squared, right? X is an exponent of 9, so now x is exponent of 3 squared. Now, here's where our rules come in. What do I do when I'm taking a power of powers? What am I doing when I take the power of powers? Am I adding, subtracting, multiplying, or dividing? A power of powers, if you forget, that's right, give you an example, and we forget oftentimes. If I say x squared times x cubed, this is x, 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 x. We have x to the 2 plus 3 is x to the 5th, right? We can just jump there. So if I'm multiplying powers, we add the exponents. But if I say x squared cubed, this means I have 1, 2, 3 sets of it. That's what an exponent does. Okay, I'm saying I have 3 sets of x squared. Well, this becomes x to the 6. A fast way is x to the 2 times 3. If I'm taking the power of powers, we multiply the exponents. If I'm multiplying powers, we add the exponents. So this is a totally 2 different things going on. So if you forget, come up with an easy example for yourself, write it out so you don't get it wrong. So what am I going to do here with this 2 and x here? What am I going to do with the 2 and x? Am I adding, subtracting, multiplying, or dividing these 2 and x? This is the power of powers. This is like this guy here. And that means we're going to multiply them. 3 cubed is equal to 3 2x. Okay. Now, given this problem, we can see that, well, we both have the same base. Well, the exponents now have to be equal then. Fine. We're going to set the exponents equal to each other. 3 is equal to 2x. We can divide both sides by 2. X is equal to 3 over 2. Now, is that right? It's a fraction. So let's go ahead and double check this. Now, this is taking us pretty much all the work we've been doing the second semester about exponents. Let's see if we can get that. 27, is this equal to 9 to the 3 over 2 power? Now, we have to rewrite this to make sure we're correct in the good. Whenever I have a fraction, that's a radical. So this can be rewritten as a radical of 9 cubed. Is that okay? You guys see how the fraction is really a radical? If you remember that from before? Hopefully you do. What's the square root of 9? The square root of 9 is 3. And 3 cubed is 27. So 3 over 2 is that exact answer that we wanted. So some of these problems can get even more like infuriatingly like confusing. Because like this one itself was, how am I supposed to get 9 to become 27? You're right. How are you supposed to do that? And this is where us playing with exponents, playing with the factors, getting them to have the same base. And you can see there's no calculator needed here. I don't need a calculator. Our other methods will require a calculator, okay? Our other methods will require a calculator. But us not having a calculator, we can still easily solve this using find the same base. Okay, let me give you another one. The problem is 64, 3x minus 3 is equal to 4. This one looks crazy, okay? This is just nonsense. How can I get 64 to look like 4? Now, if x was 1, sure, if x was 2, if x was 3, right? Maybe I can start guessing, but what if the answer was a fraction? I'd just be wasting my time. So what can I make them both look like? Can I make 64 look like an exponent with a base of 4? Or do you want to make them both look like 2s? And now it's your own personal choice because both of them would have worked out. So if I want, I'm going to go ahead and make them into base of 4s because let's see, 4 times 4 is 16. And 16 times 4 is 64, okay? So if we have 3 4s, we're in good shape. So that we're going to rewrite this so that they both have the same base. 64 is really 4 cubed. And then 3x minus 3 is equal to 4. And I'm going to write a 1 there so you guys can see that I have 1 4. Now, please notice that I made 64 into 4 cubed. And this brings us back to our last problem. Hey, now that they both have the same base, what do I do to those exponents, the 3 and the 3x minus 3? We're going to add them, subtract them, multiply, divide. Hopefully you remember the rule. If I'm taking the power of powers, exponent of an exponent, we multiply those. 4, 9x minus 9. Because we're going to multiply everyone by 3. We're multiplying that, we're going to distribute that 3. Oops. Equals 4 to the 1. Now that we have the same base, we can have the same exponent. This implies that this is that 9x minus 9 has to equal to 1. Has to, must, no choice. Great, now we're at 9x minus 9. We can solve it algebraically. This takes us back all the way to August of what, for you guys, 2018 or something, right? So plus 9, 9x is equal to 10. Divide by 9, divide by 9. Oh my goodness, x is equal to 10 over 9. Would you ever have guessed that? I would not have ever guessed that. Nor do I want to guess that. Okay. And that's the fraction that we would need to take this 64, 3x minus 3 to bring that shrinkingly back to 4. Okay. Now, is this our own way of solving it? Answer is no. We could have used a calculator. Now, this method is, and on SAT again, in standardized tests, sometimes they say no calculator, and this method would be used for no calculator. Trying to get them to have the same base, and then I can make the exponents the same, right? And this is a great hint. I remember when I saw this in high school, I was like, how can I make 64 look like 4? And the trick is to make them have the same base. So how can we solve the same exact answer? Actually, let's solve the last two answers. Okay, let's solve 27 to become 9x. So 27 equals to 9x. How can I solve this algebraically? Well, we can do it two different ways. We can do the identity way. Let's first jump into the identity. Circle of logs. Log, what's my base? Is my base 27, 9, or x? The base, hopefully you can see, is 9. That's the base of the exponent. The answer is 27, and we're solving for x. As you can see here, using the identity is a super fast way for us to set this up. And we just have to type on the calculator log of 27 divided by 9. Log of 9, sorry. And that'll give us our answer. On a calculator, let me go ahead and see if I can take a calculator without adds. It's probably going to show up with adds. We're going to see 27 log. Remember, on my calculator, these cheap calculators, you have to type log first, divided by 9 log. And we end up with 1.5. 1.5 is the equivalent to 3 over 2. So if I have a calculator to do the work for me, great. But if I write log of 27, if I go 27 log, 0.84, am I going to be able to like keep that in my brain? No. Even if I write that down as 0.845, the decimals are going to round off incorrectly and I will never get 1.5. It'll actually be 1.5 blah 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 blah, right? So if I just wrote 0.845 divided by, let's do 9 log. I'm warning here that this is the warning, right? Warning is if you don't have if you do use the calculator incorrectly, you're not going to get the right answer anyways. Whoops, 9 log. I did 9 log, right? 9 log is 0.95, is that right? Let's do 27 log again. I'm not sure if I did that right. 27 log is, well, sorry, 1 point, my numbers are off, that's why I was like, it didn't make sense. 1.431, right? If I divide this 1.431, 1.431 divided by 0.95. See how that's 1.506? You probably would have wrote this not realizing it was just 1.5. And it's because if you try to write down these numbers, you're not taking the complete number. And when you're not doing it in just typing this in the calculator, it's going to mess you up. And you might enter 1.60, so 1.51, and that will give you the wrong answer, and they would mark you wrong. And it even won't be even a choice for multiple choice. So you have to know how to do this in this correct method. Okay, so this is a big no-no because you lose too many decimals along the way. Okay, now here's our method that we're working on today. Okay, so we worked on identity before. Now we're going to work on it, solving this algebraically. So here's what we're going to do. We're going to use a common log to solve these. 27 is equal to 9 to the x. Now, if I walk into the room and I see this problem and I have a calculator with me, again, I have a calculator with me, I can say, well, if I'm solving for exponents, what tool do I need? Okay. If I see a nail on the floor, what tool do I need? If I see a nut that looks like this, okay, what tool do I need? So it's all about looking at the problem and saying, what tool do I need? In this case, to solve for exponents, I'm solving for x and x is an exponent. I need to use logs. So let's use common log. Let's use common log. And this is one of our easiest ways to solve for these. Not much thinking, we just use the same method. 27, okay, we're gonna log both sides. Log of 9, x. Now, why do we even use logs? Remember I joked around the log is like a ladder, my log ladder, it's gonna help me reach for that exponent. So what happens is this exponent gets brought down. Log of 27 is equal to x log of 9. What happens, remember, logs bring down exponents, it brings down the gods, and it's brought down to in its human form. Now that the problem is no longer an exponent, this is just multiplication. And I can deal with multiplication because the opposite of multiplication is division. There is no opposites of an exponent, right? You could, if you knew what the exponent was, sure, the opposite of a square is a square root. The opposite of a cube is a cube root. But the opposite of x root, what is this, like a movie, x root? Is this like Groot? I am Groot? Hope not. So then now we can divide this by log of 9 because log of 9 is just some decimal number that I don't care to memorize. So x is equal to log of 27 over log of 9. And please realize that is the same answer that we got using the identity. The identity is our fast way, and this is kind of our proof of how we got from our exponential form into our log form. And this is our proof behind it. Now, can I do this with almost any problem? Sure, yeah, why not? Okay, why not? Why can't you do this with any problem? If you're trying to solve for exponents, you could log both sides, bring down the exponent. Now, what if I throw some gunk in the works? What if I throw something like throw some shade in it? And then what if I give you some extra trash lying around? For right, 9 is equal to 8, 4 to the x plus 4, okay? Now looking at this problem, you're like, okay, there's a lot of stuff going on. And what are we solving for? We're solving for which variable? You want to make sure you identify that quickly. I'm solving for the exponent. So if I'm solving for exponent, I'm probably going to use logs. Now, you cannot log when there's too much stuff going on. There's too many people at the party. So we're going to ask some people to leave. Who should we ask to leave? The 8 with the exponent or the 4, which is just a common 4? Get rid of the commoners first. Come on. The slubs can stay as long as they want. So we're going to get rid of this 4 because opposite plus 4 is minus 4. That's kind of easy. 9 minus 4 is 5. 5x to the, is equal to, 5 is equal to 8 to the 4x power. Now we're stuck here. How can I get 8 to look like 8 to look like 5? You can't, right? So we know this answer is going to be some type of fraction decimal. So let's go ahead and finish it off. So from here, you can do 1 or 2 steps. You can either jump to the identity, circle of logs, log, base what? Base 8 of 5 is equal to 4x. We could do that, but I'm going to go ahead and work through our log way of solving it, okay? This is identity method, which is not wrong. Identity. Okay, sorry, I can't spell. Now, we're going to log both sides. 8 to the 4x. What happens to the exponents? Remember, the reason why we're using the log, we're using our log ladders, right? We're going to go up there and bring down the exponent. So we're left with log of 5 is equal to 4x log of 8. Okay. We're going to get rid of some numbers here. I'm going to get rid of the log first, and I'll worry about the 4 later, because it makes my calculator work a little easier. Log 5 divided by log 8, right? I'm dividing both sides by log 8. And we're left with 4x. Just to make this a little easier for you, you could take the 4 with you. If you guys want to take the 4 with you, right? But I'm showing you guys how to just do this separately. Now, calculator work. What's log 5 divided by log 8? That's not going to be a nice number. It's going to be some decimal. Let's go ahead and type that out. 5 log. Here, log, 5 log divided by 8 log. Bam. We have 0.77. And now you could write 0.77 here. You could. But I'm going to go ahead and divide both sides by 4 anyways. And divide this by 4. Oops, darn it. Clear this. We have this number. Copy. Yeah, paste it again. Come on. Apples. Go figure. See, it would have been faster if I just typed the whole thing. Never mind. 5 log. 5 log divided by 8 log. I try to do things a fancy way, but nope. And we're divide this by 4. And we end up with the answer. X is 0.1935. Let's do 4 decimal places. Okay. So we have our answer. Our guess is a 0.1935. Now let's go ahead and double check if this answer even worked out. If I say 9 is equal to 8 to the 4.1935 plus 4, will that give me something close to 9? I have no clue. Well, okay, I hope it's yes, okay? So we're gonna say, on this calculator, I need to type it, in which way? I need to type it, you see the XY button over there, right here, see XY? We're gonna use that button. So we type 8XY, I'm gonna do a parentheses, 4 times 0.1935, close that parentheses, equals, right, that's close to 5, and 5 plus 4, 9, and a bunch of decimals. Perfect. That's exactly what we were hoping for. So we were able to solve for the X value that would get us really close. Because of round off error, we're a little bit off, but it worked for us. Okay. All right, so we have one more type of log that we can talk about, and that's exponential e, okay? So we're gonna have problems with e now. E to the x is equal to 5. So if I say what x value would get you to 5, you could use log, sure, but we have a special type of log for this, and we've talked about this before, hopefully you remember. This is log, log e, natural log. This is called natural log for us. So ln is our fancy way of saying natural log. Okay, and this stands for log base e. So instead of common log, log is what we call common log. And it is log base 10. Okay. Now we can use them interchangeably. You can use log base E if you want, log base 10, you can log whatever log base you want on the calculator. But for this one, to make our lives easy, we're going to use log base E. Now let's go take a look what happens when you do use log base E. Well, what happens when you use the same base of any log? If I say log base 3 of 3, well, what is the answer to 3 to what exponent gives you back to 3? 3 to what exponent gives you 3? 1, right? Log of 5 to what exponent gives you 5? Well, log to the 1 exponent. So essentially, I want you guys to think of these as the way they cancel out. They just cancel out. Okay, so that's going to be important to us. Because if I could pick the right log here, if I write log e of e to the x of log e, hey, aren't these supposed to just cancel out? You guys ever watch those Looney Tune cartoons where like Wile E. Coyote like disappears all of a sudden, boom, right, in a flash, and there's like whatever's left over here. Let's say it's a bomb, right? So Roadrunner will disappear and there'll be a puff of gas, and then he'll disappear. What happens to the bomb? It falls down, and then Wile E. Coyote, how does he look? Something like that. Okay, and then he has big eyes now because he sees a bomb that's going to fall on top of him, right? So it just falls to the ground. That's essentially what happens. Once we get rid of the log, the x just falls to the ground, and we're left with log base e of 5. Now, we don't write it this way. We write it using natural log. So we're going to do the same problem now in a pretty form. E to the x equals to 5. We're going to natural log both sides. Natural log both sides. And just as a reminder, exponents go to the front, or we can just drop them. Both ways work. Instead of doing all this writing, we shorthand it with just the letters ln for representing natural log. So log base e is represented by natural log. So this is your work for this problem. If I don't see this work, I don't give you credit. I need to see that you are actively doing the inverse, which is the log, natural log to both sides, and that's how you're going to solve it. And then you just have to type natural log of 5. Let's give you guys another problem. What if I write e to 2x plus 1 is equal to 4? Okay, so we're solving for x. We can't do natural log. We can't do logs if there's too much stuff going around, right? We gotta get rid of those commoners. Ask 1 to leave the party. See you later, 1. E to the 2x is equal to 3. Now that we have e by itself, we can now use natural log. Why am I choosing natural log? Because the base is e, and we have a special log for that. Right? This is our VIP guest here. Hello, E. Welcome. We have your room ready for you. So natural log to both sides. And when I natural log both sides, this e is going to cancel out, leaving me just a nice 2x falling to the ground. Last step, divide both sides by 2. X is equal to natural log of 3 over 2, not natural log of 3 over 2. Make sure you don't stick that 2 in there. It's natural log of 3 over 2. You don't have to write a parentheses, but you have to make sure you have the understanding that it's not, we can't just mix those together, right? It's an ln of 3, then divide that number by 2. Let's show you guys on the calculator. Just show you, make sure that those numbers are not the same. If I say 3 natural log, then where's my natural log? Natural log, then divide that number by 2, we get the answer of 0.5493. But if I do 3 divided by 2 first, and then 3 divided by 2 first, and then natural log that, oh darn it, come on. 3 divided by 2 first, and then we natural log, that number is not the same, okay? That's not the same piece, and you would get the answer totally wrong. So make sure you know the difference. The 2 happens after we natural log both sides. Now, let's go ahead and solve for a kind of difficult problem now. And this is a half-life problem that we're going to be working up to. if I give you 1/2 is equal to e to the k of 320. Okay, if I give you this problem here, how would I solve for k? K is in what position? K is in the exponent. Now, how do we solve for exponents? What special tools have we been working with to solve for exponents? Well, if it's up high, we need a ladder to get there. Hopefully you have a wooden ladder around. We'll use a log ladder, okay? So we're gonna use logs to solve for this. So let's go ahead and do that first step. We're gonna log both sides. Which special log can I use for e? Do I want to use common log or do I want to use a natural log? Let's use natural log here. So we use natural log 1/2 is equal to natural log e to the k 320. What happens to this natural log and the e? We said those cancel out. This drops to the ground. Natural log of 1/2 is equal to k. You can write it the other way if you want, but 320k, right? It's like Thanos snapped his fingers and half the world disappears. Half the equation disappears when natural log snaps his fingers. Now we're almost done. We just need to divide both sides by 320. So k is equal to natural log of 1/2, all divided by 320. On our calculator on the right, that's exactly what we're going to write. 1 divided by 2, which is 0.5, that might save you time. Natural log that. And then we're going to divide this by 320. Okay, and that's our answer, our k value. Okay. Now, if you don't find that difficult, our next section is going to be working on exponential growth and decay, and really that is the algebra 2 in it. If you can do that, you can do all these word problems, no problem. Okay. And that's us working on natural logs. Okay, and that's it. Oh, one more thing real quick, a couple things just to remind you about logs in general. If I say, for instance, 1 is equal to 4 to the x, what exponent of any number makes you back to 1? Oh, how I got, okay. So a question was, how did I get this answer of negative 0.00216? I typed this in my calculator. I did 1 divided by 2 first. Let me clear that. 1 divided by 2 first equals 0.5. I natural log this number. And once I have this number, I'm still going to have to then divide by 320 afterwards. Then divide this new number by 320. And that's how I ended up with this number here. And that's what k is equal to. I shoved everything here inside the calculator in the correct order. Okay, great, perfect. Now, just a reminder, anything that goes to 0, no, anything that goes to 1, exponent is going to be 0. So I can automatically say x is equal to 0. But that's it, you don't believe me. Okay, it's 4 to the 0, that's 1. Anything to the 0 power is 1. But let's say you don't believe me. Fine, let's go ahead and write log of 1 is equal to log of 4 to the x. Where does the x go in the front? Log of 1 is equal to x, log of 4. So log of 1 divided by log of 4 is equal to x. Let's see what happens when I write 1 log. 1 log 0. Really? 1 log is 0? What about 1 natural log? That's still 0. Anytime you take a log of 1, it's going to be 0. So it's x is equal to 0. Now, why is it, again, why is the log of 1 0? Let's rewrite this. Log of 1 base 10. Why is it 0? How can I make 10 become 1? What exponent of 10? 10 to what power would be 1? 0. Wait, no. Yeah, that's right. 10 to the 0 power is equal to 1. Okay, and that's one of the reasons. All right, that's it.